look at how they wrote f of x was the derivative. What's kind of weird about that compared to what we did last chapter? It doesn't have a prime symbol. So there are going to be times where it's going to seem a little goofy. If they tell you that this is the derivative, the original is going to have a capital F. So you just have to be ready to see different things like that. If you do go on and take more math, notation is going to be part of the big thing about it. So we have little f of x is our derivative. We want to go backwards to the original to get our capital F of x. Okay, so now let's think about going backwards. 3x squared. What would we have derived to get 3x squared? Bring something down to the front, subtract 1 from the power. What did we do that to? X cubed. So this is what I'm going to write. That's an original function. Can anybody come up with another answer?
Yeah. No.
There is one.
Yeah. Oh, it's probably like a third or whatever. Not square root, but.
Oh, I know what you're saying. Not quite on this one. Anything else we could have derived to get 3x squared? You want me to give you a one to get your minds going? Why? The derivative of what is 0? Let's get more general. A constant. So could this also be 1? Could this be 1? When you go backwards, there is an infinite amount of answers because of that constant. Now, I don't want you to spend your whole life giving me all the answers. So what we're going to write is this as our answer. And that C represents any constant. It doesn't matter right now what that constant was. It just could be anything. Maybe it was a 0, but maybe it's 512. Could it be a negative? Sure, a constant can be a negative. You could add a negative number. So we're going to call that a general solution. And that's one of the major differences between derivatives and integrals and antiderivatives. When you have antiderivatives, they give you a whole family of answers. And so we're going to be working with that. Okay, next thing is we're going to look at this problem. We're going to try to solve another one. We're going to find the general solution of y prime equals 2. Okay, so we're going to practice our notation too. We're finding the general solution. They're telling us to go backwards. So if they're telling us the derivative is a y prime, what would the notation be for the original? Y prime is the derivative. Go backwards to say y equals. Can you think of what you derived to get 2? You want the general solution. I don't like it. Because I like 701. So we're going to put plus 2. So whenever you go backwards, with your general solution, you put that plus 2 to represent that whole thing. No, because we're going to eventually find the specific family member, but we'll have to have more information. So when we're going with general solutions, always a plus C there. But we're going to find particular solutions in a little bit. Anything else at this moment you want to ask about before we delve a little bit more into notation? Okay, let's talk more then about some of the notation. Okay, so for this, let's review the symbol we had for a derivative. Do you remember that? dy over dx. They would say, like, find dy over dx, and they're telling you to find the derivative. Bless you. Well, according to that first thing we had in our notes, this also could be what a derivative symbol is. Okay, now let's just think basic math. This is like a fraction right here. If I want to solve for dy, how do I get dy all by itself? Did you follow me on that, or you have a question? No. Okay, now, this is all about going backwards, right? So if I have the derivative of y, what's the original symbol going to be? The derivative of y goes backwards to y. Okay, now, this little symbol is not truly a math symbol. That means go backwards, in my mind. Forward and go backwards to y. Then, we want to take this and go backwards. And this is the symbol for going backwards. You might have noticed this at some point. Anybody see that squiggle? That's what that squiggle means. It's telling you to go backwards. It's an integral symbol. I don't know if you've talked to other people in AP Calc or what's in your book, but now we're entering the land of the squiggle. And that just means we're going backwards. Okay, now I'm going to take this and just kind of label the parts. So this is an integral symbol. This f of x part is what we're going to call an integrand. And then the dx part tells you what the variable of integration is. So those are the three parts that we're going to be working with this whole chapter. An integral, an integrand, and the variable of integration. Now, this is telling you to go backwards. So when you go backwards, you'll get your general solution that looks like this. So you go backwards from little f of x to big F of x. And then we always are going to add c for our family. And this, if you see the word, just so you know, this is the constant of integration. So when you hear integrate or antiderive, they mean the same thing. They're synonyms. Here's what we're going to be working with. Another word that you're going to see is indefinite integral. And that's just kind of what that whole symbol means right there, that all packaged together. Ethan. The capital F in this case means original. This is the derivative going backwards to the antiderivative. And it's just another way they show it. And I think like in higher maths, I don't know if in high school, but in college they might use that capital F, which is I think why they introduce it here. Other questions?
Like that whole thing.
That whole thing, like let me get a different color. Let me go yellow. The indefinite integral is like this part right here. Other questions before we kind of practice a few? Okay, now we started off with some easy ones, like going backwards from 3x squared and 2. But you had to kind of think. Wouldn't you like a couple rules so you could just apply the rules over and over again? I thought you might. Austin's not so sure.
You say like quotient stuff?
Oh. Huh, I don't know. How are we?
Like chain rule?
You gotta learn all that all over again? Okay, well, we're gonna go over them. We're gonna practice and practice and practice and practice. But I do want you to know in your textbook, there's a whole big gray chart of all kinds of rules. So if you need to see it a different way than us practicing it, you can look on page 250. There's all kinds of gray technical boxes. But our most common one that we're going to start off with is what we're going to call the power rule. So we had a power rule for deriving. Now we're going to have another one for integrating. And here's what it's going to look like. Okay, so we've got our integral symbol, our integrand, and this tells us our variable of integration. If we want to go backwards from this, here's what we're going to do. This is going to be the rule we can apply. What did they do to that power? Added 1, and they divided it by the new power. That one is going to be the one we play over and over again, is this power rule. Okay, so let's try one out. Let's have x to the 7th dx that we're going to integrate. So we want to go backwards from x to the 7th. So add 1 to the power, which is what? And then divide by that new power. And then, depending on if we want a general solution or not, we're going to add c. So this one is our whole family. We're always going to do c right now. Now, especially in the beginning, you're going to kind of question yourselves. So if you want to check, like when we're going to have a quiz this Friday, you're still at that checking point, derive this, and you can see if you get back here. You can kind of go backwards and forwards and check your work. So do you remember how to derive now that you've been anti-deriving today? Remember how you bring the power to the front and subtract 1 from the power? So you bring an 8 to the front. What happens with those 8s? They cancel, and then you have x to the 7th. So you can always check these to make sure you did them right. Okay, let's do another one. Let's do... What's that answer going to be? There we go.
Oh, yeah, I definitely believe that. I put 8 there.
Oh, it's only 315. You could do it with fractions. That brings a good example. I'm so glad you said something, Mason. Let's make it 2/3. Okay, add 1 to the power. 2/3 plus 1. 5/3. Divide by that power. Now we're going to fix those because that's a fraction in the denominator. So instead of dividing by 5/3, you multiply by there's your answer. I'm glad you said that. So we're dividing by that new power, but I don't want a fraction in there. So you multiply by the reciprocal. All right, what about this one? Can we use power rule? Is that a power in there? Yeah. What power is that?
Oh, okay.
Positive 1/2. Okay, so add 1 to 1/2. So you got x to the 3/2. Divide by 3/2, but that's the same as multiplying by, there we go. Yeah. Then add 1 to the power. Okay, what about this one? Because we'll be getting some trig in here in a little bit. Get some betas. Okay, now, this is telling you your function, beta squared. This is telling you your variable of integration. So all it did is it changed your x's for a theta. You still follow the same rule. You take this, add 1 to the power, divide by the same power. So this will be theta cubed over 3 plus c. So even if they switch variables on you, it's okay. That'll just get us ready for when we deal with other stuff. You could have t's in there, you could have w's in there. This just tells you what you're you just want to stick with x. Alright. Okay, power rule so far, are we okay on power rule? Okay, there's another rule we're going to move on to next. And let me just write this out like this. So this is more than power rule. What's kind of messing us up? What's changed besides just a power rule in there? That's 6. What kind of words? There's all kinds of words we could call that, but what's one thing we could call that 6? Coefficient. Anything else we could call it?
One more than 5.
Okay. Very creative. We've got a leading coefficient, we've got a constant multiple, a scalar, all those kinds of things. We're going to do the same thing we've been doing with constants all along. They just tag along. What you can do is you can just even bump it out to the front if you like to see it like that. This is the constant multiple rule, if you want to name. And then that constant just tags along like normal. That 6, just keep it going. And then integrate, we're going to be multiplying by what's the antiderivative of x squared using power rule.
Why is it?
And the 6 just tags along, and now we're going to integrate x squared. So we just multiply it by the answer, then that can simplify to, and there's our answer. So when you have a constant, you just multiply it through. Just keep it going. That's fine. Let me give you another one of those. Let's have this. Try to write the whole final answer before we talk about it. Can you do this one? There's our answer. Okay, you want one more of these before we think about something else? Or are you good on this so far? Okay. Alright, now, what if I did... There's no x there, but I could put an x there. If I put an x there, what power would it have to be to? That changes it. Yeah, because what's anything to the 0 power?
Oh, you're talking about if it was just 4?
Oh, yeah. So isn't 4 times x to the 0 still just 4? So think about power rule here then. I got a 4, add 1 to the power, divide by the power, which is 4x plus c. Does that derive to give me what I started with, a 4? Yeah. So if you have just a constant, you can either think about that or you can just know it goes back to that x. So like what is the integral of 3.2? Good. 3.2x plus c is the answer. Okay, now let me give you this one, because this one's a little bit tricky. Nothing's in there. Almost. When they don't put anything in there, 1 is always our placeholder. So what is your integral of 1? So this is x plus c. So that one's a little tricky because you're not sure what they want in there, but 1 is always a placeholder. Okay, let me see. Bless. All right, let me give you this one. Okay, now, just like when we were deriving, you cannot do power rule until that power is in the numerator. So you got to fix it first. So how do I fix it so that power is in the numerator? You'll also notice when I rewrote it, I didn't get rid of that because I haven't anti-derived it yet. I just rewrote it. Then we can apply power rule. So add 1 to the power. What's negative 4 plus 1? Good. And then you know we have to fix those negative exponents. So I've got to bring this down. And there's my final answer. Those are the ones, especially when we're beginning, take your time on to watch the signs and that kind of thing. Now, another thing I want to point out, notation-wise, is properly for integrals and antiderivatives, the notation is a bookend. You have to have the squiggle and the dx part. If you forget the dx part, it's wrong. Those are bookends. They'll mean more, like if we would get to chapter 7 or something, it has a deeper meaning. But you have to keep these two parts when you go to write things and that kind of thing. All right, let's try another one. Let's do okay, can we do power rule yet? No. We need to bring that 3 up. This is what we have to be careful with, though. Only the x cubed comes up. The 2 doesn't come up with it. So this is the same as writing this. And then that 1/2 tags along. And then add 1 to the power, divide by the power. And that's going to be our answer. Okay, let me give you one to try on your own real quick. Let me do this one. Try this one. Do you know how to do it? Could you have the negative on the bottom? Yeah. The negative can go top or bottom. Just one of them, though. Okay, do you want one more of these, or do you want to go to the next rule? You tell me how you feel. Next rule? Next rule. If you have multiple things going on in there, so you're adding or subtracting multiple things, well, like everything else, you can split them up. So we can have the integral of x dx plus the integral of 2 dx. We split them up with everything from limits to derivatives. We always treat them individually. Okay, so what is the integral, the antiderivative of x? And then we add in the antiderivative of 2. Okay, that constant. What's that go back to? What's 2x? They would probably consider the sum or difference rule. Now, let me think about this. I don't want to leave it like this. Let's say this constant was 4 and this constant was 3, and I add them together to get 7. Is that still a constant? If this was 2 and this is negative 5, they combine to be negative 3. Was that just a constant? If you add two constants together, you're going to get just one constant. So we always only ever want one C. Don't put two C's in your answer, because they would just combine to give you one whole C. Now, I'll tell you this. It's up to you when you get better and you get faster at this. You don't necessarily have to do this in between step. You could just go from here if you're comfortable with that. Integrate this, integrate that, add your C. Okay, let me give you one to try. Let me give you a sum or difference one. Try integrating that. Bless you. Are we good? Okay. Not too bad, I know. This homework won't take so long. You'll get in the groove. Okay, here's another one. Nice little power rule. But remember, you can't do power rule until it's in the numerator. So how can I rewrite that? Okay, now you add 1 to the power and you divide by the power. That's not an answer.
Oh, sounds like it does.
It exists. Okay, now let's think about this. This is the one time power rule does not work. Okay, I'm even going to erase this. When x to the first is on the bottom, power rule is not going to work. One exception. Okay, so let's think back to the whole year, or actually just the derivative part of the year. Do you remember what we derived and got 1 over x as our derivative? You're on the right track. Natural log. Remember way back when you had the natural log of x, the derivative of that was 1 over x. So now we have the derivative. It goes backwards to the natural log of x plus c. Now there's one tweak we have to make to this. The natural log function is always positive. So we have to force this x to be positive, so you're always going to put absolute value signs around that when you go backwards. So that's the one time. It's the weird natural log one. If you ever see x to the first on the bottom, it's going to be a natural log. Yeah, and you have to put those absolute values. Okay, now let me just do one other thing with this. Let's say we had 4 over x. Is that going to be a natural log problem? Yeah, because it's x to the first on the bottom. 4 is just a constant multiple. So 4 just tags along like always. And then the derivative of that x on the bottom is this. So there's the goofy one.
How do you know the natural log?
When we did natural logs, you always did 1 over the inside stuff times the derivative of the inside stuff. So 1 over x ended up being our derivative of this. So when we see 1 over x, yeah, so that's the same as this. Okay, let me do one more right here as is. Let's put a couple things together. Let's do one more big one I'm going to have you try, and then we'll look at our test. Let's try that one. And if you're not sure, take your final answer and derive it. See if you get back to the question. All right, anybody want to ask a question before we finish that? Okay, then what we're going to do, I'm going to write down your assignment on the board. It's back here too. This one seems like a long assignment, and the reason why is you got lots of little things like this, so they don't take you that long. That's why there's going to be a lot of numbers. I'll write that on the board. You can get that, and then I'll pass back your Chapter 3 tests. I'm not entering the tests in until we get a couple more buffer things, just if it wasn't your best grade. We'll get some more buffers in there, so it's not the only grade. And then we'll have a quiz on this section Friday. And remember, Wednesday is a 2-hour delay. So that's in our future.
What?
Yeah.